Hello, everyone. Welcome to the webinar on characterizing and optimizing new generation solar cells and OLEDs. My name is Faridi, and I'm Regional Manager at Nano Vacuum company. I joined Nano Vacuum about 4 years ago after finishing my PhD in micro-nano fabrication from Monash University. Nano Vacuum, as most of you may know, is supplier of nanofabrication systems to our customers in academia, industry, and government. We have the pleasure to present FLUXiM company in Australia and New Zealand. FLUXiM provides Swiss-made software and hardware on OLEDs, displays, and solar cells. Our speaker today is Dr. Daniele Braga from FLUXiM. Dr. Braga earned his PhD from University of Paris with main focus on organic field effect transistors and organic solar cells. Dr. Braga was a postdoc researcher at the University of Minnesota in the USA and the ETH Zurich University in Switzerland. That's where Daniele and I were working together for years. After that, Dr. Braga moved to a high-tech startup, Femtoprint, where he was able to develop an innovative femtosecond laser printer to fabricate micro device out of glass. Currently, he is the head of sales and marketing at FLUXiM based in Switzerland. At FLUXiM, he supports researchers in developing perovskite solar cells and OLEDs with FLUXiM software and hardware. I leave the rest to the expert to introduce the products from FLUXiM. Please feel free to type your questions in the chat or raise your hand if you have any questions, and we will answer all of the questions at the end of the talk.
All right, great. Thanks, Ava, for the introduction. As Ava said, my name is Daniele, and I'm a member of the sales and marketing team at FLUXiM. Our company, FLUXiM, is based in Switzerland. It's based in Switzerland. Give me just 1 second. Our company is based in Switzerland. It was a startup spinning up from the University of Zurich, the Department of Physics, in 2006 from Professor Rustaller. Since then, the company has been developing several tools, as Ava said, to help researchers working on LEDs, in particular organic LEDs and solar cells, on emerging solar cells. At the moment, we have a total of 6 in between instrument and software, and today I'm going to present our researchers are using this tool to develop their own devices. As I said, the motto of the company is the tools that boost your R&D. R&D on displays, on solar cells and batteries. In particular, if you have a look into an OLED display, like in this case, this could be the screen of an iPhone or any other phone in which they are using organic light-emitting diodes, you will see that this is made of an array of pixels, red, green, and blue. Every single pixel is a light-emitting diode, and this light-emitting diode as a stack of materials. You're injecting charges, electrons and holes, you're emitting photons. So you can start with our tools to ask yourself how this device, this LED, is behaving inside this matrix, and try to optimize the matrix because you're trying to optimize the behavior of the single LED. The same thing can happen if you're working with a solar cell. A solar cell is a stack of materials in which you are absorbing photons and generating charges. And then on that case, you can ask yourself how this device is going to behave given a particular stack of materials. How do I scale up the device moving forward from the lab scale dimension to the large area solar cell, and how this device is going to behave when it's incorporated into the solar panel. These are all the questions that we are trying to resolve, to give an answer to by using our tools. And today we are going to focus on this class of devices, particular solar cells. When you're developing a solar cell, surely you can ask yourself, how do I improve the device efficiency to make these devices competitive with existing commercial technologies? You're working maybe on the device at the lab scale, so the small area device, you're trying to improve the efficiency, you're trying to improve the stability of the device. And after that, there is a next round of important question you need to resolve. How do I scale up the device by maintaining the performances, the efficiency of the lab scale solar cell? Everyone knows that when I'm increasing the lateral dimension of the solar cell, then the PCE, the power conversion efficiency, is going down because I have parasitic resistance, I have several different losses, and I need to try to find a way to reduce these losses. So when we are developing solar cells, emerging solar cells, there are several different researchers working in the field. Everyone has his or her own needs. Researchers, they have different approaches. There is Paul who would like to characterize solar cells and extract parameters. Elena would like to simulate these devices and try to optimize virtual devices with simulations. Larissa is interested in scaling up the device. Tom, Lynn, Michael, researchers that maybe are interested in how stable is the device, how well could I characterize the device with my tools. Finally, there is this Michael who's trying to use machine learning to analyze and understand what the data are telling me. So if we are starting from researchers, experimentalists, a researcher working in the lab, this Paul could decide to use a simple instrument to perform current voltage characterization on one solar cell. Or he could decide to analyze the solar cell, the single solar cell, more in details by using a combination of different experiments, up to 12 or 13 different experiments, which are going to give a better idea about the physics of the device itself. There is Tom is going to perform current voltage characterizations or MPP tracking, stability analysis at constant voltage and constant stress, constant current over 32 solar cells. Or you could also decide to combine several instruments together to get a better understand of the physics of the degradation of the devices themselves. So he's stressing the devices, and then meanwhile, he's performing advanced characterization to understand a little bit more why the solar cell is degrading. There is Lynn that decided that performing one single current voltage characterization on one solar cell is not enough. She would like to do 56 current voltage characterization on 56 different solar cells at the same time in parallel. So if we start from the high throughput characterization by using 12 different analyses, everyone working in a lab knows that this is what can be done or is done, a combination of different instruments with a lot of different cables. This approach is time consuming. There are different instruments that are probably calibrated, but their calibration is different because the instruments are different. There are RC effects of the cables. So at the end of the day, this is surely not an ideal solution for a combination of multiple experiments. What we try to resolve this issue by developing this tool called BIOS. BIOS performs DC, AC, and transient analysis on solar cells or LEDs. So you could have a combination of different analyses all together in the same instruments. This instrument is calibrated down to the probe tip, and this assures you that your collection of data is reliable. You're not moving the cell, you're not touching the system. The instrument is starting from the first measurement. It's performing all the measurement in cascade. You will have all the set of data analyzed by the software, you could really consider this one as one block of experiments on the same device, because you are not touching the device once you started the first measurement. Here, a real is a full characterization of perovskite solar cells. The paper is from 2019. This is a perovskite solar cell, different JV characteristics with different scan rates to study hysteresis effects, and several other experiments in between capacitance versus frequency, impedance spectroscopy, IM-PS, which is intensity modulated photovoltaic spectroscopy, and so on. So this was Paul. We said that Lynn, she's interested in performing JV characterization in parallel over multiple devices, multiple solar cells. We have an instrument called LithoSlide. What you need is surely a sample order designed on the customer layout. Every solar cell is going to be in contact with one measuring unit, one SMU. With this instrument, you can really study your devices, changing parameters in your device, and then have a real statistical analysis of the different parameters of your solar cell. So you can get the JSC, the VOC, the fill factor, the PCE of different devices by changing, in this case, one of the parameters of your fabrications experiments. And at the end of the day, what you are going to get is a true statistical analysis of your solar cells. Why? Because all the measurements are performed in parallel under the same conditions. Before you can report, as I said here, all the parameters by giving the reader the spread of the data that you collected during this single experiment that you performed. Tom was interested in the stability of perovskite solar cell. So you will need an instrument that could both do this JV characterization in parallel. So he will be able to provide the same data that Lynn was providing, the statistical analysis of the different efficiency parameter of the solar cell, and also tracking the MPP, performing the full MPP tracking on the different devices, constant voltage stressing and constant current stressings. Right, great. So this part was a characterization of solar cells. After the characterization, so once you have the data, this experimentalist could ask for some help to Celine. She's a researcher interested in simulating devices, virtual devices, fitting data with a true model that is getting inside the device physics and trying to extract the actual parameter of the devices by performing simulations. And this is what she's doing. She's taking experimental curves and then using diffusion equations and to fit the experimental data. We developed already more than 10 years ago a software which allows you to calculate and to study light penetration in the solar cells. So, emerging solar cells with a stack of different materials, and this software is telling you where the photons are going to be absorbed. Then these photons are going to be passed to diffusion equations. You have exciton generation. If this is an organic solar cell, for example, then exciton dissociation. You're bringing in the exciton, the charges in the drift diffusion equations. At the end of the day, Selina is able to reproduce the JV characteristics that the other colleagues or herself obtained in the lab. She's also able to reproduce the trend of the current density versus the thickness of the active layer in this specific solar cell, and then predict how the current density is going to evolve if I'm increasing the thickness of the active layer even further. This was an old result. What a researcher at KAUST did recently, is working on and developing an organic solar cell with a power conversion efficiency of over 17%. They've been able to actually fabricate the devices and then analyzing the JV characteristics with SETFOS, simulating the JV characteristics, and then predicting how the JSC is evolving while I'm increasing the thickness of the active layer. This is a similar example of what we reported before. Once the model is calibrated, you can, for example, study how if I'm changing the active layers, because I'm changing the band gap of the active layer, how the PCE is going to evolve. This can be calculated, and I can even play further and calculating the evolution of the PCE versus the different variables in my solar cell. For example, the mobility of the active layer, the thickness of the active layer, and so on. I can even study what is going to happen to a tandem solar cell, tandem organic solar cell, with different energy, different band gap of the two subcells. So when I have a tandem organic solar cell, I could take the experimental data. These are the JV characteristics of the two subcells, the red and the blue. This is the JV characteristic of the combined tandem organic solar cell. This is the schematic that we have in the simulation software. The software is able to reproduce perfectly the JV characteristic of my tandem solar cell and the two subcells. Now the model is calibrated. I could start play around as I did before, maybe a little bit better, a little bit with more in details. I can sweep the thickness of the active layer in the bottom cell, active layer in the top cell. Then I'm going to find a maximum of power conversion efficiency, either with a pure optical simulation or a combined electrical and optical simulation. The two maximum are different because the two simulations are at the end of the day different. These are organic solar cells. Recently, the community started to work on a different type of tandem solar cell, which is a perovskite-silicon tandem PV. Already 5 years ago, we developed this software SETFOS. We have a module called Advanced Optics, studying scattering at the different interfaces in the tandem solar cell or at the anti-reflecting coating that you are adding on top of the solar cell. And the simulation, again, is telling you that, for example, like in this case, without any structuring of the solar cell, the reflection is a lot. So this green part of the EQE is giving you the reflection, the total reflection of the solar cell. The JEC, because of this light reflection, is lower than the JEC of an optimized solar cell, in which the reflection is lower because I've been adding some structures. For example, as I said, in the anti-reflection coating. So the model and the experiments are fitting well. We have the structure A. This is a silicon perovskite tandem solar cell with no structures. There are a lot of losses, as we see here in the CQE. The fitting and the experiments are well done. When I'm increasing the amount of complexity in my device, I'm adding structure to both the anti-reflection coating and to the bottom cells. I'm increasing the JSC, as we have seen before, and also the EQE is way better than before. And again, the fitting and the experimental curves are matching well. Now, again, I have the model, then I can start play around increasing the complexity of my structure from a non-structured solar cell to a fully structured solar cell in which every interface has been structured. Surely there is a lot of scattering there, but then the EQE is of this solar cell, of the fully structured solar cell. This one is showing way less reflectance, for example, with respect to the planar solar cell that it was taken as a reference device. These are data that were in the literature from the Fraunhofer, and we perform all the simulation on these different devices. So now, Selina did a lot of simulation. Paul did the experiment, and there is a tool from FLUXiM called the SetFos-Pios integration, and another called Pios-SetFos integration, which allows you to pass experimental curves from the CS, the characterization suite, that is the software performing the experiments, to SetFos, which is the software performing the simulation. There is a full integration in between these two software, which allows these two collaborators to work together. Paul is using Pios, is performing the experiments, is performing also some analytical fitting of the data, whereas with a combination of SetFos and Pios, the collaborators can dig into the physics of the device. In this case, for example, we have a PIP device, PIP junction, JV characteristics or capacitance versus frequency. We would like to understand what is going on in this device. So we perform a SetFos simulation. Now we know that in the steady states, the whole density is distributed in this way versus the position in the device from 0 at the electrode to 100 at the other electrode. But we can also analyze the capacitance frequency curves. And now we have a color plot, frequencies versus position. We have the whole density, and here Selina, the collaborator, is able to understand that charges at low frequency are going inside the device, whereas at high frequency, they are accumulated at the electrodes. This was done on an organic device. We can do the same on a perovskite solar cell. In this case, we need a drift diffusion equation for both electron and holes, but also for anion cations. We have a Pios measurement, we have SetFos simulations, and a different preconditioning of the solar cells, or different steady state voltage. We have a different distribution of the ions inside the active layer. Then really on this solar cell that we have seen before, we have seen the black curves where the experiments. Now we have all the simulations performed by the other collaborators. The simulations are perform exactly perform at the same time with the same set of data. All the experiments are performed with the same machine, so I can really take the full package and be sure that this belongs to the same device. And what I can do is really, this is the key, the extraction of single model parameters set via a global fitting. What does it mean? That now I can really perform a global fit of all the experiments that I perform with the same machine, with Pios, by using the same software SetFos. What I can get at the end is what is called a correlation matrix. Why this thing is important? Because with a large number of unknown, getting accurate extraction of fitting parameters is very difficult because the parameters are correlated. This means that if I just have a JV characteristic and I'm fitting this GV characteristic, I have different variables. If one of these variable, for example, is going up, the other one is going up again as well, I will have the same effect in my JV characteristics. As in this case, the injection barrier at the cathode and the injection barrier at the anode are highly correlated. It means that if I'm changing this barrier at the cathode or I'm changing the barrier at the anode, I'm going to see the same effect. So I don't know what is happening in my solar cell if I'm performing only one experiment. Now, if I'm using as in this case, more than 12 experimental techniques to analyze the same device. Now my matrix is showing that my variables are not correlated anymore. this value close to 0 means my different variables are not correlated. Now I can really give one number to the different variables that are in my fitting. How do we do this? So in SetFOS, we are using several methods. Some of them are local optimization, several methods for the fitting. Some of them are local optimization. One of the most important is this famous Levenberg-Marquardt algorithm, the gradient methods. But one problem of this local optimization method is if you have different variables, you could always land on a local optima. And this probably is not the best optima that you can get. So we have also global optimization methods, simulated annealing, Bayesian optimization. These are the most famous that we are using. And this is the availability of both methods is very important when you are performing fitting of the data. In some cases, Levenberg-Marquardt is, by the way, what we have been using for the generation of the correlation metrics that I've been showing before, because in this case, we can get the Jacobian. Now, another example in which on the other side we are using the global optimization method is when we need to study perovskite-silicon tandem solar cell, in which we have a constraint. The current that is flowing through the two subcells needs to be the same. So in this case, not going into the details, but in this case, the local optimization will not work because there are minima, the target function is not differentiable. So the global method can be used in particular when I'm, for example, sweeping the thickness of the magnesium fluoride of the perovskite reactive layer. I could have simulated the maximum current that I can obtain from the stack. The two global optimization methods, the Bayesian optimization and the simulated annealing, are going to give the same results, but as is clear here from this graph, the Bayesian optimization is going to converge way quicker than the simulated annealing, which is trying a lot of different points in order to find the global optima. Great. So we've been discussing about the needs of these different researchers, experiments, simulation, performing stability analysis, or collecting JV characteristics in parallel over multiple solar cells. The last request that we have from the researchers is this Larissa. She would like to scale up the cells to modules. She would like to start from the lab scale device, increasing the lateral dimension of the device, but she knows that when I'm trying to do that, the power conversion efficiency of the device is going down. We developed this tool called LAOS. It's a software based on the finite element methods. So a particular software using a 2D plus 1D approach. What does it mean? That we are resolving the distribution of the potential at the electrodes by using FEM. And the two electrodes are coupled by what is called a 1D coupling law. Therefore, most of the time, the JV characteristic of the ideal device, of the JV characteristic that you find from, for example, BIOS from an experiment on the solar cell at the lab scale. Why does it work? Because the conductivity at the electrode is order of magnitude bigger than the conductivity of the active layer, and the lateral dimension of the electrode are way bigger than the thickness of the active layer. So now with this tool, this researcher could ask herself how the key parameter of the solar cell depends on the electrode layout, the dimension, the position. So she could optimize the large area solar cell by optimizing, for example, the layout of the electrodes. So she studies how the lateral dimension, the conductivity, the reflectivity or the transmission at the electrode is influencing the characteristics, the efficiency of the solar cell. she could find a maximum of power conversion efficiency versus the width of the metal finger at a certain transparency of the electrode and a certain conductivity. And everything can be done with the software instead of spending the time in the lab and performing multiple experiments, trying to scan all the different parameters, trying to optimize the width and length and transmission of this electrode experimentally in the lab. This can be done with the software. And now we go to a real case. We collaborated with this company called Organic Electronic Technology. They fabricated flexible solar cells. This is called a solar umbrella. We can simulate, we have the layout, we can import this layout into the software. There are metal fingers here. This is the typical P1, P2, P3 structure, and we are importing this structure into the simulation software, and we can reconstruct the JV characteristic, but moreover, and most importantly, we can calculate the distribution of the electric potential inside this mini module. Now, this is how the electrical potential goes into the mini module. We know where there are potential drops, and we know how is the effect of the parasitic resistance in this mini module. For example, we can try to optimize the configuration by changing the layout, by changing the lateral dimension of the single cell in series, for example. This was the electrical steady state model of Laos. It's, the models is usually resolving ohms, using the ohms equation. What we also have in Laos is an AC module. So we are going to the frequency domain. Instead of having just a DC coupling, we also have an AC coupling. But we also have two additional modules, thermal steady states, so using the Ito equation, and the other one, thermal AC, that I'm going to show you later why this is important and for what we are using it. So now a few examples to show how Laos is used. The electrical steady state should be to reconstruct the JV characteristics of the mini module, optimizing the layout, as I said before. Electrical AC, now we have access to the frequency domain. We are reproducing the impedance data from mini module, where we are changing the electrode sheet resistance. So we could also understand what, for example, in the electrode sheet resistance, we could have pinholes, so we could have some shorts in the other electrodes, and this can be simulated also with the software. At thermal steady state, we are simulating IR images. This we all know that are important because they are giving access to shunts. The shunts are bright spots in the IR camera, but the IR image as shown here is very blurry. So recently we developed another technique called small signal dark locking thermography technique. Actually, we didn't develop the technique, but we developed a software that goes that is coupled to a camera. Now we have access to the amplitude and phase, the signal given by this mini model provided by SEM in Switzerland. The phase itself is very well resolved. We are able to simulate the signal, and we are able to identify shunts, bright spots in the. Therefore, we are really having a picture showing how the solar cell, the mini model, looks like. And with this, I'm going to conclude my presentation. I hope it was clear enough. I've been able to show you that there are several researchers with several needs, and FLUXiM is trying to provide a tool for everyone. And to conclude, I left over this. Michael is interested in machine learning to analyze and understand data. This is what we are doing at the moment. We are working on some tools that would allow the analysis of large magnitude of experimental data. And yeah, thank you for your attention. And you will find all the information that I presented today on our website, fluxim.com. Thanks.
Thank you so much, Daniele. It was a great talk. Do we have any question? Please feel free to raise your hand or type your question in the chat.
Okay, open the chat. The characteristic of the light source compared to actual sun. Yeah, that's a good question. It depends on which instrument you're referring to. In PIOS, we are using a white LED or an array of monochromatic LEDs. This is not compatible to a sun simulator, not at all a EM 1.5G. Why? Because we need to have a pulse LED. We are performing transient analysis, so we need something that is switching on and off fast. And the transient LED, the pulse LED that we are using as a rising time standard of 100 nanoseconds. We also have a nanosecond pulsar, which has a rising time of 5 nanoseconds. This is what allows you to do this transient analysis. A solar simulator will be too slow to do that. The instrument, the little slide, is on the other side combined to a solar simulator, different LED-based solar simulators. This is why? Because there we are interested in performing JV characterization. So we need a solar simulator. In one case, we're even using an LED solar simulator in which you can upload your own spectrum. So you can, during the experiment, change from AM 1.5G to AM 0, or if your solar cell doesn't behave well on AM 1.5G, you're just uploading an indoor spectrum, and then you're using that to characterize your solar cells. There is another, what's the parameter varying frequency from 10 Hertz to 10 millihertz? Not sure I understand this question. It really depends on what you're referring to. Maybe I can try to search. Generally, what we are reporting here is the impedance. This PIOS has a frequency range from 10 millihertz to 10 megahertz. Also, this 10 millihertz and 10 hertz, as you're referring, is very important when you're studying the impedance of the solar cell. There are a lot of information there. I don't see any other question, but
If we don't have any question, then...
Okay, yeah, there's another question. In case of OLEDs, is it possible to get some idea? Sure, this is possible. As I said, this instrument PIOS does all this set of characterization on both solar cells and LEDs. Then the configuration of the instrument is different. For solar cells, we are using a pulsed LED, pulsed white LED or monochromatic LED, as I said before. For LEDs, we are having the instrument is controlling a photodiode and a spectrometer. So there, it depends on what you want to see, which experiment you would like to perform. For transient experiments, again, you're using a photodiode because the spectrometer will not be fast enough. But also the spectrometer is important. You could study, for example, the dependency of the light emissions versus the per light voltage, or yeah, there's a question from Vinesh.
Hi. So my question is, what are the sample requirements for PIOS and LITOS? Is there a particular sample size, contact footprint, and contact locations that you need?
Yeah, that's a great question. PIOS is coupled to a small probe station. Let's call it like that. It's a table with probes. And with a carousel that is moving under the solar cell automatically, all the different tools that you need to characterize either the solar cell or the LED. So there are not really limitations on the dimension of the solar cell or on the position of the contacts, because you have a probe station, right? You can move the different probes. You have also in the instrument, you have a multiplexer. So you can connect the instrument to different probes and you can therefore connect the instrument to up to 4 solar cells and perform all these experiments sequentially over 4 different solar cells. Litho slide on the other side as a custom-made sample order. So also there are no really limitations, because we are fabricating this custom-made sample order for you, for the customer. Is a work that we do. We are getting the layout of the user, the customer, and we are fabricating this sample order specifically for you. The lateral dimension or the active area of the solar simulator, you have 2 choices. So this is going to give you the total exposed area, 5 by 5 centimeters square for this solar simulator, plus A++, whereas we have a larger solar simulator with an active area of 16 by 16 centimeters square, which is class AAA.
Thank you. And I have another question, but I will wait for my turn again.
Please ask it.
Yeah, sure. Thanks. So when you're measuring a tandem solar cell, do you need individual cells data, or if it's a 2-terminal tandem, are you able to extract the bottom and top cells performance individually?
If you need to perform a simulation with samples, it's always better to have the JV characteristics, at least the JV characteristics of both solar cells, individual solar cells. This is because at the end of the day, it's better to calibrate the model. So if you're able to then simulate, as I've been showing in the presentation, the JVs of all the solar cells, the 2 subcells and the tandem, then you're able to get a better calibration of the model and then a better extrapolation of the data that you need to extract.
Okay, so the software does take care of the differences when they combine together in electronics and also optics. Is that am I understanding it right?
Again, now it depends on what we are talking about. If we are talking about the characterization of the solar cell or the simulation of the solar cell. Before I was referring to the simulation. So the simulation of the tandem is better to have the JVs of the different subcells. For the characterization of the tandem solar cell, then most of the time you don't have the 3rd electrode. It will be better to have it. Then the characterization itself, it works exactly in the same way if you have a tandem or not, meaning that when you have access to the 2 contacts of the subcell, then you're collecting the JVs in the same way. One thing that you need to be aware of is that in PIOS, we are using a probe station. So you have the contacts on the same side, and this is most of the time not the case on a tandem solar cell.
Okay, thank you.
Yep, sure. Yeah, there's another question. Wonder if other solar companies are going this deep into R&D. That's a great question. And the simple reply is, it depends on the research field. It depends on the size of the company. For example, in the OLED business, these big corporates are developing OLEDs. Yes, they are going this deep into R&D. They are using a lot of tools, a lot of simulation tools to really dig into how the OLEDs is behaving, how the OLEDs can be optimized. The reason is also that you can imagine an OLED, a commercial OLED could have 15 or more materials stacked together. characterizing these devices could be very difficult, and therefore a simulation software, for example, is required. On emerging solar cell, again, it depends on the size of the company, it depends on what they are developing. Some companies, honestly speaking, they're not really interested in going this deeper into R&D. Why? Because they are trying to rush into the development of the most efficient solar cell, or the most efficient large area solar cell, the most efficient modules. But some of them are doing that. For example, this company that are trying to optimize the layout of the solar cells or the large area LEDs. Also, in that case, they are interested in optimizing it with simulation software. Right, I see there is a Binesh.
Hi, so me again. So we have projects in solar cells and organic LEDs. So this simulation tool set force, does that work equally for both solar cells and LEDs, or do we need an additional packages for one or the other?
Yeah, that's another good question. SetForce has 4 different modules. If you're working on solar cells, you're choosing either 2 or 3 of these modules. If you're working on both solar cells and LEDs, you are going to choose 4 of these modules, meaning modules are emission, absorption, drift diffusion, and advanced optics. The emission is really the model that is going to be used for the community developing OLEDs when you want to simulate how this device is going to emit light. Absorption is telling you where the photons are going to be absorbed. Drift diffusion is the module that is resolving the drift diffusion equation to study the electrical properties of your solar cell or LED. The advanced optics is an optional module. There we included basically scattering, let me call it in this way. So if you're developing tandem solar cells, you are also interested in this advanced optics, because you need to include scattering at the different interfaces of the solar cell, or as I showed before, on the structuring of the coating, for example.
Thank you.
Sure.
If we don't have any other questions, then I'm sharing 2 email addresses in the chat. In case you have any question in the future or you need more information, feel free to contact us. And thank you everyone for joining us today. Thank you so much.
Thanks, Ava. Thanks, everyone. Have a nice day or evening.